All right, guys, now that we have gone through a review of basically phasor arithmetic and also sinusoidal steady-state analysis, in which we took the original circuit and then looking at the sinusoid's angular frequency and then converting all the capacitors and inductors into their impedance equivalents, and then solving the circuit essentially with DC methods, we're now ready to talk about basically power within a circuit and definitely an AC system. And so for the next few minutes, we're actually just going to be looking at base concepts of what power is before we even start looking at how to solve for power within that system. So by now, you guys should actually be working through the rest of the problems, working through practice tests, and really getting comfortable with performing basically essentially DC analysis methods within phasor arithmetic to essentially be able to find voltages and find currents appropriately. Looking through the practice test really will help for that. Now, power is not something that we discuss too much within circuits 1 because in terms of circuits 2, we actually reinforce that. Now, power by a base definition is essentially the rate at which energy is actually being expended within an electrical system. So the base equation for that is always going to be P is equal to V times I, so voltage times current. And within a DC system, it's always measured in watts. However, when we take basically instantaneous power and consider that with the introduction of alternating current within the circuit, then as we have said before, if we introduce a voltage that is sinusoidal in nature that has an angular frequency, omega, whatever value of voltages across elements or even the current through the elements actually end up being will also be of a sinusoidal nature, same cosine waveform, and also the same angular frequency. So when we consider what we call instantaneous power within the system, we say instantaneous because we can determine whatever the value of that rate of expenditure of energy is within the system at any given point. Then we can actually say that P of t is equal to V of t times I of t. Now, in this case, guys, if we say, oh, well, we're just going to take the voltage and multiply it by the current, then essentially what we have done here is said that we're going to take a sinusoidal voltage and multiply it by a sinusoidal current. So Vm cosine omega t plus theta v times Im cosine omega t plus theta I. Now, if we go back to the idea of multiplying sinusoids together, it's not as straightforward as just saying, well, Vm times Im and then cosine omega t plus theta v and do something with theta I over here. We actually have to apply a cosine identity for this, which we actually take two cosines in which we actually have to consider two differing arguments. And the differing arguments here, omega t plus theta v, is definitely different than for the current omega t plus theta I. So the way that we actually can do the appropriate calculation for the instantaneous power within any AC system is to basically just say cosine A times cosine B is actually equal to 1/2 cosine A minus B plus 1/2 cosine A plus B. Or in other words, what we're doing here is actually saying we're taking the argument of B and subtracting it off from A for the first portion, and then for here, we're actually adding both arguments together. Now, when we actually apply this identity here, so that we can appropriately go ahead and multiply these two sinusoids together, then essentially what we get is the following. P of t is equal to 1/2 Vm Im times cosine omega t plus theta v minus omega t minus theta I. And over here we have 1/2 Vm Im cosine omega t plus theta v plus omega t and then plus theta I. And the result from applying this identity is essentially the following. What we get is essentially 1/2 VMIM cosine theta v minus theta I, because basically omega t from this portion of the argument actually cancels each other out. And then right here we actually see we get 1/2 VMIM cosine 2 omega t plus theta v plus theta I. And instantaneous power is in fact actually measured in watts. But what does the result of applying this identity actually really give us? So here, if we actually consider 1/2 VMIM cosine theta v minus theta I, what happened is that basically time got canceled out within this portion. And so essentially 1/2 VMIM cosine theta v minus theta I is essentially nothing more than a scalar value. And over here, we see 1/2 VMIM cosine 2 omega t plus theta v plus theta I produces a sinusoid that's actually double the frequency of which we actually had for originally the voltage and the current within that system. For whether we're looking at the source or we're looking at a specific element within that system. Now, what we actually find here is not only do we have a DC portion, essentially, of that power, but then we also have a sinusoidal portion of that power that constantly gets cycled back and forth from the source to whatever load element that we're actually delivering that power to. And if we look at this from a graphical standpoint, that sinusoidal nature here is actually offsetted by some form of DC portion here. And what that means is that essentially that DC portion, or what we actually determine as the average below the curve, or average power below the curve, is actually something very significant to us. And essentially what this represents is the power that we actually utilize or absorb within that system. Any absorbing element that we actually deliver this power to, this is the power that's of use to us. Average power, that DC offset that actually causes everything to shift up. So average power is generally what we mainly concern ourselves with in an AC system. This sinusoidal portion is definitely present, and is definitely of concern to us. But this average power portion is actually what we always have to map to. Now, since we've actually gone through and had a discussion concerning basically sinusoidal steady state analysis and how to find voltages, how to find currents within a system, that discussion and the work that we've done with that has set us up for actually doing true calculations in terms of the AC system, looking at the power that we actually are going to be calculating throughout that system, and being able to determine essentially also that system's efficiency. So, how do we actually utilize the phasor arithmetic methods and then actually map essentially to this average power? This is actually what we really concern ourselves with, because if we already have a method of multiplying and dividing cosines, then we actually don't need to keep going back and forth to this. The only thing that we need to make sure that we do is actually provide a method that maps directly to basically this portion of the instantaneous power, that DC offset, that average power, 1/2 VMIM cosine theta v minus theta I. This is the one thing that we need to make sure that if we're utilizing phasor arithmetic as a tool to make our calculations within sinusoidal steady state analysis easier, then we need to ensure that our calculations for power within phasor domain is actually mapping back to this appropriately. So I'm going to take the camera just on a little bit of a walk, and we're going to go that way. So. All right. And some of you probably already recognize a portion of this board up in the top right corner. And let's see here. Okay. So, guys, when we go back and we talk about the average power within the system, that average power, that's incredibly important to us. And any type of calculation that we do within our system to determine that power always has to actually map back appropriately to basically 1/2 Vm Im cosine theta v minus theta I. Just in our discussions within basically the chapter 9 and chapter 10 work, or even going back to our discussion with differential equations and the technique of utilizing Laplace transforms, whatever we're doing in order to actually make our calculations easier and the tools that we actually utilize, everything that we do has to map back to the time domain. Remember, everything that we do is 100% just a simplified variation of basically calculations that we would do otherwise in a more complex manner. So let's see if we can develop a tool that would actually allow us to appropriately map back to 1/2 Vm Im cosine theta v minus theta I. So what we're going to start talking about, since we've been working with complex numbers, we also can represent, instead of instantaneous power, we can have something called complex power. Complex power basically just saying that we're utilizing complex numbers in order to perform basically some mapped calculation of that power. And since we're utilizing impedance, the impedance values that we have within the system for inductors and capacitors naturally introduce complex values of power in terms of those calculations. So let's take a look here. Let's see if we can derive something that would map to 1/2 Vm Im cosine theta v minus theta I. Well, power is equal to voltage times current, right? Okay. Let's see if that works. So V, if we took basically the phasor equivalent of V of t and I of t, so therefore we get Vm at angle of theta v, and then Im at angle of theta I. So P is equal to Vi. Seems, I don't know, seems like that could work. So let's check this out. Vm at angle of theta v multiplied by Im at angle of theta I. Well, let's see here. If we take two phasors, and those phase angles, we actually add them together, then all of a sudden, if we just say V times I, then we get 1/2 Vm times Im at an angle of theta v plus theta I. That doesn't look the same to me. 1/2 Vm Im cosine theta v minus theta I. Is that the same? Well, I mean, that's the equation. P is equal to V times I, but it didn't produce 1/2 Vm Im cosine theta v minus theta I. It produced Vm Im at an angle of theta v plus theta I, which the real portion would actually just be Vm Im at an angle of theta v, of cosine theta v plus theta I. So it doesn't work. In fact, actually, this is just total crap. That's bad. No, doesn't work. This equation no longer is applicable to us when we're dealing with phasors at all. So this is bad. No, we do not use this. Not at all. So how can we actually develop an equation that appropriately maps back to this form, 1/2 Vm Im cosine theta v minus theta I? Well, here's where we actually introduce a couple of new terms here. So instead of actually having V times I, complex power, or what we now denote as S, is actually equal to 1/2 V times I conjugate, in which we actually take the phase angle of the current and we negate it. So here, 1/2 Vm at an angle of theta v, and then we multiply that by the conjugate of Im at an angle of theta I. So essentially from there we get 1/2 Vm at an angle of theta v, and then multiplied by Im at an angle of negative theta I. Now we know with polar numbers that those phase angles add together. In this case, we're going to add together theta v with also negative theta I. So essentially, when we perform this calculation, we get 1/2 Vm Im at an angle of theta v minus theta I. And once we expand that by Euler's identity and convert this over into its rectangular form, then S is equal to 1/2 Vm Im cosine theta v minus theta I plus J 1/2 Vm Im sine of theta v minus theta I. And that right there, folks, actually shows that the real portion, based off the conversion into the rectangular form from Euler's identity, in fact actually does go through, and this portion maps right back to the average power. The average power being 1/2 Vm Im cosine of theta v minus theta I. So essentially what we get this real portion that sure enough maps back. But we also don't just say that that is average power, we also say that that is what we call real power. And real power within complex power is actually measured as watts. Now, what's this over here? Well, by a natural notion of having basically complex impedances for basically capacitors and inductors, then just simply by the use of inductors and capacitors within any electrical system, when we're utilizing phasor arithmetic, we're actually going to also come up with this portion of the complex power that we have to deal with that is actually what we call reactive power, or Q. And the difference by Euler's identity is that we get 1/2 Vm Im sine theta v minus theta I. So the reactive power, or Q, in fact actually is the imaginary portion of the complex power. And we measure that in terms of bars. So essentially S is made up of what we call real and also reactive power, or real power and the imaginary power. The imaginary power is essentially what gets cycled back and forth from the source to the load. And the real power is essentially what is being burned up in terms of the resistance within that system and actually being absorbed. This is the portion that we are really, really concerned with. And this is the portion that we always have to map back. But note here that the complex power calculation here, the equation that we have, we actually had to derive just in the same way that the Laplace transform was actually had to be derived in such a way to map back to what's really going on in the time domain. It all maps back to that time domain calculation. So if we consider that S is equal to P plus JQ, then if that's made up of watts and var, then the actual units that we measure complex power, and some of you guys may have actually already seen this if you work at TVA, is that here we measure that in terms of volt amperes. Volt amperes. And again, that's made up of real power and reactive power. Now, what does this do to the system? And what does that do to the efficiency of the system? Well, let's take a look at how we can visualize real power and reactive power. And if we look at the total power within the system, volt amperes, is basically what my old mentor, Dr. Haskell, said. He introduced it to us in this very simplistic way, that we have a glass of beer. So if we have a glass of beer here, and we fill it up. Now if we're not talking about, if we're talking about watered down Meisterchow, like you don't want that foam on the top. But what does the foam represent, and what does the real beer represent? Well, if the total power within the system is representative of that glass of beer, then the real power is the beer that we actually like to drink. And the reactive power is essentially that foam on top. That's useless to us. Unless we have a Russian Imperial Stout, then that little bit of foam on the top is actually really good. But for the most part, we want to actually pour our glass of beer with the least amount of foam on the top, the least amount of reactive power. And so that reactive power that we get within this system is naturally just made up of essentially a byproduct from utilizing capacitors and inductors within a system. So from here, we can actually visualize that real power is actually what we really want to have within the system, just like when we want to pour a clean glass of beer. And we're actually going to be learning later on down the road this semester about how we can actually mitigate that foam on the top, that reactive power, that power that we actually don't need. Okay? So before we actually get into showing a calculation of power, we're going to talk about convention. I'm going to make this really, really simplistic. So much of the time we're actually not going to be utilizing S is equal to 1/2 V times I conjugate. We're going to talk about a convention that is essentially used within industry, why it's actually used, and why it's actually going to map back appropriately to this equation here. Is that it's going to allow for ease of calculation, and from here on out we're going to utilize these forms in terms of actually calculation within the system. So I'm going to maneuver the camera down one more board. All right. So essentially, when we want to map back to S is equal to 1/2 V times I conjugate, we're going to start looking at something that's called the RMS, and that stands for root mean squared, or what essentially we call effective value. Now, what is RMS? What is the effective value? And essentially, these are standards and basically more so a convention that we utilize to basically make our calculations of real power very, very, very easy. And essentially the values of magnitudes that we actually utilize from the RMS value of voltage or the RMS value of current would essentially be a scalar value that we could essentially say would produce the same amount of real power if we utilize some DC equivalent circuit. And so all we would actually have to take is the magnitude of the RMS voltage or the RMS current, multiply those two together, and then we actually get effectively the real power within the system. It gives basically folks within the industry a very, very quick and easy way of just finding out what real power is actually being dissipated. As far as the reactive power within the system, we're going to talk about that a little bit later when we start talking about power factor, and also when we start talking about power factor correction. And those concepts are way more indicative of essentially the efficiency of the system, how we deal with the efficiency of the system, and how we can actually correct it. Now, so the RMS value, again, this is essentially the magnitudes of these values here would actually allow us to easily calculate the real power within the system. But here, all we have to do if we want to convert a non-RMS circuit into its RMS value is basically take the magnitude and just divide by the square root 2. Now, same thing applies to the current as well. We would just take the magnitude divided by the square root 2. And so by that notion, the complex power equation, S is equal to V RMS times I RMS conjugate, actually produces the exact same solution as the complex power that we would have utilized with the equation of 1/2 times VI conjugate. Now, how does that actually produce the exact same equation? Here, if we take Vm over the square root of 2 at angle of theta V and multiply it by the conjugate of Im over the square root of 2 at angle of theta I, or in essentially negative theta I, then what we get when we pull out the values of 1 over the square root of 2 multiplied by 1 over the square root of 2, we actually get 1/2 times Vm Im at an angle of theta V minus theta I. So in fact, actually guys, the RMS values still do produce the exact same thing, but the reason why we utilize RMS values is to make sure that our calculations are just a little bit more simplistic. Now, essentially, if we start off in our calculations with an RMS voltage source or an RMS current source, that means that every single current or voltage within that circuit is effectively going to have that effective value, or will be in terms of RMS. And the way that we can always ensure that we understand that our calculations are correct is just by ensuring that that is denoted up front within the calculation. So once again, and just to review, we started off with this idea of instantaneous power. How do we actually look at the rate at which energy is being expended within that system? And so we say that P of t was equal to V of t times I of t, and we said, oh, multiplying two cosines together may not actually be the easiest way of calculation, definitely not the quickest way. So we took our discussion on phasor arithmetic and then put everything in terms of their complex forms, whether it's rectangular or polar, and then we went ahead and did our calculations in a more simplistic fashion by ensuring that we mapped back to that real or average power that was in fact 1/2 Vm Im cosine theta v minus theta I. But in this case, we also want to further develop an easier way of calculating these values within the system. VRMS times IRMS. And in fact, actually, what comes out of the wall socket right below me here is in fact actually that 120 volt is in fact RMS. And you'll see that as a convention throughout all of industry. So, why don't we actually take an opportunity now to go through and actually show an example of how we could actually determine the complex power within a system. So, I'll be right back. All right, let's take a look here. So this is actually from a lab that I'm not even sure we're going to even get to do during this semester, which I'm pretty disappointed about. We were on a really good roll this semester, but you know, we got